All right, so we're going to look at the activity identifying key features of graphs. So we're going to go through some of these together, and then I will have you do some of these on your own. So these are this first page here is giving us the information that we're going to be analyzing. Some of it is pretty straightforward. A few things you might have been introduced to last year, because in Math 1 last year, you do a similar activity like this, but just for linear and exponential, since those are the only two functions that you were studying last year. Obviously, we're adding some others in, so they're going to ask you to name the family of functions, and you should be able to look at the shape of the graph to give that information, whether it is linear, exponential, quadratic, absolute value, step, or piecewise. And it says if it is piecewise, give names to its pieces, so what functions make up the piecewise. Points of interest. You're going to make a table of values. Clearly label any of these if the graph has them. X-intercepts, Y-intercepts, minimum, maximum, and a transition point if it is a piecewise function. And then going over to the right, intervals of significance. Intervals of significance are talking about your x-axis. They're talking about breaking your x-axis up into parts. The positive and negative is saying when what part of my x-axis are my y values positive, what part of my x-axis are my y values negative. And then they're also going to ask you about increasing and decreasing. What intervals is your function increasing? What intervals is your function decreasing? And we'll talk about some different ways to name those. Increasing and decreasing, we'll be talking about interval notation and inequality notation. Then we're going to talk about symmetries. Does the graph have a line of symmetry or not? End behavior. End behavior is what happens on the very left-hand side of the graph and what happens on the very right-hand side of the graph. Is my function going up or down? That's basically what end behavior is talking about. Domain and range. What are the possible x values for domain and what are the possible y values for range? Average rate of change. It's similar to the idea of slope. If it's a linear function, average rate of change and slope are the exact same thing. If it's not a linear function, then again, it goes back to an interval. We can choose a section of the x-axis and find out what the average rate of change is for that function. But the only time that the average rate of change and slope are the same thing is for a linear function. And then identify the equation. Use all that we know to write the equation of the function. So those are the different things that they're going to ask us to do. So we're going to turn the page and we're going to start with graph A here. So what is the name of the family of functions for this first graph? Just looking at the shape of the graph, what type of function are we talking about here? This is the linear function. It's a straight line. So we should be able to recognize graphs based on their shape. So this would be a linear function. Now for end behavior, I'm going to show you how we're going to write this. We're going to say as x approaches either negative infinity or positive infinity. Just to remind you, negative infinity is to the far left of the graph. Positive infinity is the far right. For the x's, for your y's, up is positive infinity and down is negative infinity. And we're going to be talking about those directions a lot as we get into these different problems that we're going to look at today and tomorrow. So how we write this, we say as x And I'm going to say the word approaches, but instead of writing out the word approaches, we use an arrow. So as x approaches negative infinity, f of x approaches, and again, instead of the word approaches, we use that arrow. So f of x, remember, is the same thing as saying y equals. So what we're saying in this, as my graph, as my x values move to the left on this graph, the further left I go, are my y values positive or negative? Do my y values go up or down on the far left-hand side of the graph? They're going down. They're going down, that means they're approaching negative infinity. So as x approaches negative infinity, f of x is approaching negative infinity. Because as I go to the left, I'm going down. Left and down are both negative infinity. And then the second one we say, as x approaches positive infinity, f of x approaches what? So as I go to the right, are my y values going up or down? Up. So as x approaches infinity, f of x approaches, what one goes with up? Positive infinity or negative infinity? So as x approaches infinity, f of x approaches infinity. It will not be where every function they approach the same direction. Sometimes yes, sometimes no. Depends on the function. Now, domain and range is an idea I know you've been exposed to in the past. I know last year you studied linear functions specifically. Domain, again, is all your possible x values in a function. So my domain for a linear function, and this actually applies to any linear function. Does anybody remember what the domain of a linear function is? And again, what this is asking, is there any x values that I can't use? And there are not any. So we could either say, you could write out all real numbers, or you could use interval notation, which in this case would be parenthesis, negative infinity, comma, positive infinity, parenthesis. So when you see negative infinity, comma, positive infinity in parentheses, they're telling you that's an interval, which means there's no restrictions. It can go on as far left as you want, as far right as you want. Remembering that graphs don't stop where our grid stops. Our grid is only showing a snapshot of the function. Unless they very specifically put endpoints on your graph, graphs continue beyond what we see. In a linear function, range follows the exact same way. There's no restrictions on any y values. So again, I could say all real numbers. Or again, I could write this in what we call interval notation and say negative infinity, comma, infinity, to show that all values are possible. Now, for points of interest, I have to look at my graph. On a linear function, there's usually a lot of points that you can list. I mean, I see -2, -8, -1, -6, 0, -4, 1, -2, 2, 0, 3, 2, 4, 4, 5, 6, and even all the way up to 6, 8. So we're going to create a T-chart here. And you will discover different functions. There are some functions we're going to look at in the next couple days where we can only get 3 ordered pairs off the function because of the way it behaves on the graph that we have. So linear functions, you can usually get more. So -2, -8, -3, -6. -1, not -3. Going the wrong way. -1, -6, 0, -4, 1, -2, 2, 0, 3, 2, 4, 4, 5, 6, 6, 8. So those are all different points that I can identify on my graph. And like I say, depending on the function, will depend on how many points you can identify. So now, once I have that list of values, now they want me to look, do I have any x-intercepts in this graph? Do I have any x-intercepts here? Do I cross the x-axis? Yeah, so right here at 2, 0, there's an x-intercept. And I see it in my table here. And what about y-intercept? 0, -4, that's where I cross the y-axis. So I mark that. Zero, -4 is my y-intercept. Because it's linear, I don't have a minimum or a maximum, and it's not piecewise, so I don't have that transition point. So those two that we've already named and shown in our chart are the only 2 points of interest for this particular function. All right, if we go to symmetries, linear functions are not symmetrical for the most part. So we would just say none here. We don't have a line. There is not a vertical line that I can fold this graph on and have the left side map onto the right side. That would mean we had some symmetry. We do not have that here. All right, intervals of significance. When is the graph increasing? When is the graph decreasing? When are the y values positive? When are the y values negative? Those are the things they're talking about here. Now, on a linear function, it is either always increasing or always decreasing. It doesn't have both. We will see functions that have parts that increase and parts that decrease. But in this case, as we move from left to right on this graph, is constantly going up. So this would be increasing. So when we talk about those intervals of significance there, and we talk about decreasing, well, in this case, this graph is never decreasing. It is always increasing. So we would say never. We don't have an interval to show that it is decreasing, and increasing because it is always increasing. This is where we would use that interval notation to say parenthesis, negative infinity, comma, infinity, parenthesis. That shows it's constantly increasing from as far left as you can go to as far right as you can go. This graph is always going up. Now, your x-axis is what determines when your y values are positive and your y values are negative. So my y values in this case start out negative because my graph starts low, and they stay negative until I hit that x-intercept. Once I hit that x-intercept and I continue on in my function, my y values go positive. So how we write this? So negative so the negatives start on the far left. So again, the negatives start at negative infinity, but they stop at 2. When I hit 2 on that x-axis, my negative numbers stop. And then my positive, in this case, because of the type of function, my positive numbers start at 2 and then go to infinity. So the interval negative infinity to 2 is when my y values are negative, and from 2 to infinity is when my y values are positive. So really those are tied back to my x-intercept. The increasing, decreasing is the general direction of the function. Now, because this is a linear function, the average rate of change is going to be the slope. Again, you can only call the average rate of change the slope when you're talking about a linear function. Otherwise, it really is just average rate of change over an interval. So again, to remind you how to get slope, y2 minus y1 over x2 minus x1. Yes, you could also get it from your table. That is another way, but just to remind you of the slope formula. So if I take any 2 points there, I can take, let's do 4, 4, and 3, 2. So that's going to give me 4 minus 2 divided by 4 minus 3, which gives me 2 over 1, or just 2. So that is my, in this case, the average rate of change is the slope. You will see as we go on to some other functions where we can only do a section of the graph for average rate of change. That too applies to the entire graph. For everyone, I go up 2 units and across 1. All right, so the last thing left here is to write the equation. Again, it's a linear function, so it's y equals mx plus b. So the slope we found right here. So we already have the m. The b refers to our y-intercept. You told me my y-intercept was here, so that's going to fill in the b. So I have y equals 2x minus 4 as my equation. So in finding the different information or the key features of this graph, on a linear, it leads you right to the equation. I realize on some of the other functions we might have to do some additional work, but it does lead us to that. All right, so the next graph, graph B, we're going to skip for now. You will be doing that one, but we're going to skip over graph B. And then graph C, what type of function would we call graph C? It is not piecewise. This is a step. I just wanted you to identify that. We're actually going to skip this one, but you should still, by the shape of it, be able to recognize that that is a step function. And we're going to go on to page 27. That graph D is the next one we are going to do together. All right, so again, based on the shape of the graph here, what would be the name of this function? It's quadratic. It's a U-shaped graph, so this would be a quadratic function. So again, we're going to talk about in behavior, what happens as I go left on the graph, what happens as I go right on the graph. So as x approaches negative infinity, f of x approaches. So again, what this is saying, I'm going to the left on my x-axis for numbers that way. As I go left, are my y values going up? Or are they going down as my graph goes to the left? They're going up. So f of x would approach, again, we're talking about infinity and negative infinity. Which of those, if I'm going up, would it be approaching? Infinity. So as x approaches negative infinity, f of x approaches infinity. So now on the right-hand side of the graph, as x approaches infinity, f of x approaches what? Again, as I move to the right on the graph now, are my y values going up or are they going down? So where am I approaching? Infinity. So you notice on this one, on the end behavior on both sides, it's approaching the same direction. So don't just assume that they approach opposite directions. You have to look at that particular function. Now, we talked about domain and range of a quadratic function back in first semester. Does anybody remember the domain for any quadratic function? Are there any restrictions on the x values that we can use in a quadratic function? No, so we use that all real numbers. Or again, you could write it in interval notation and say negative infinity, comma, infinity. That means there's no restrictions. You can use all real numbers. Now for my range, is there a restriction on the possible y values for this function? What is that restriction? It doesn't go below -9. So there's two ways that we can write this. There's inequality notation and there's interval notation. For inequality notation, we would say that y is greater than or equal to -9. -9 is included because we see that we do have a y value of -9, which is why we say greater than or equal to. And how we would write that in interval notation. Because the -9 is included, and I know we touched on this in Math 1 last year, the difference between a bracket and a parenthesis. Bracket means it's included, parenthesis means it's not included. When you are talking about positive and negative infinity, because they are not a specific value, they are never included. So anytime you use negative infinity or positive infinity, you are always using a parenthesis because it's not a specific value. Here, -9 is a specific value and it is included. So if we wrote this in interval notation, we would do bracket -9, comma, and then my y values just go up from that -9. So we would say -9, comma, infinity, parenthesis. Again, that bracket around the -9 is saying -9 is a possible value. If you have a parenthesis, you're saying that it is not a possible value for that. All right, points of interest. First, we have to make that table of values. Again, we won't have necessarily as many points here, though this one there are quite a few. We have -5, 7, 0, -4, 0, -3, -5, -2, -8, -1, -9, 0, -8, 1, -5, 2, 0, and 3, 7. So we are able to identify quite a few on this quadratic here. So if we create our x, y, so -5, 7, -4, 0, -3, -5, -2, -8, -1, -9, 0, -8, 1, -5, 2, 0, and 3, 7. So those are points that we can identify from the function. But now, which of those points would we classify as points of interest? So let's start with x-intercepts. Do I have any x-intercepts on this graph? Yes, sir. Yeah, there are 2 in this case. So we have here, we have -4, 0. This is an x-intercept. And then we have 2, 0. Which is an x-intercept. And we can see those in our table of values here. Do we have any y-intercepts in this function? 0, -8 here. What about a maximum or a minimum? Do I have one of those on this graph? Again, we're at the point, do we have a maximum or a minimum in this graph? We have a minimum. What point is my minimum? What is the very lowest point on this graph? -1, -9 here. That is my minimum. What else do we call that point on a quadratic function? Whether it's a minimum or a maximum, what other name do we have for that point on a quadratic function? Yeah, that is also our vertex. We should be aware that our minimum or our maximum, whichever one it is also the vertex of our function. That highest or lowest point. We won't have a transition point because it's not piecewise. Symmetries. Now this is a quadratic function, so we do have a line of symmetry. A quadratic function is always split through that vertex. So we have this line that is cutting this graph in half vertically, creating symmetry. The value that it goes through on the x-axis is how we name the line. So in this case, it goes through -1, so we would say x equals -1. That is how we would name the line that goes through. Now, the intervals of significance are going to be a little different here because we have both increasing and decreasing in this graph. And our y values start positive, go negative, and then they go back to positive. So we have a couple different intervals that are going to happen here. So when we think of the increasing, decreasing, because this one opens upward, the left-hand side of our parabola is decreasing to start with. So it decreases until that vertex or minimum point. And then at that point it changes and my graph is increasing. So we're decreasing until we get to that vertex, and then on the other side of it we are increasing. Now obviously if my parabola opened down, that means my increasing and decreasing would flip sides as to what's happening first. So here for decreasing, so again, all of these intervals of significance are talking about the x-axis. So we're decreasing from -infinity until -1 because -1 is the x-coordinate of the vertex. So we're decreasing there and then we are increasing from -1 to positive infinity, because once we start increasing, the graph is going to keep going up at that point. Now, my y values start out positive until I hit my first x-intercept. Then they go negative until I hit my second x-intercept. So let's talk about, I'll keep it in the same order. I think I did negative first the last time. So the negative y values happen between the two x-intercepts. So my negative y values happen between -4 and 2. So from -4 on the x-axis until 2 on the x-axis, my y values are all below 0. My positive y values, the first one happens from -infinity to -4. And from 2 to infinity. So I start out positive, hit that x-intercept. They go negative for a while, hit the second x-intercept, and they go positive again. All right, average rate of change, as I've said, if it's not a linear function, it's not slope, which means we can only find the rate of change of a specific part of the graph. So in this case, we could say, well, let's find the average rate of change from 0 to 2, just that snapshot. So from the interval 0 to 2, we can still do the idea of slope to find that average rate of change. So in this case, 0 would be 0, -8 until we get to 2, 0. So 0 minus a -8 divided by 2 minus 0 equals 8 divided by 2, which equals 4. So for that small snapshot of the graph, when x equals 0 to when x equals 2, the average rate of change is 4. Now again, that can't apply to the whole graph because we know that a quadratic function does not grow at a constant rate of change. But we can look at that small snapshot of the graph and say, well, it has an average rate of change in that area of 4. And you could pick a different section of the graph and do another one. I think on the first page it said do 2 sections. We're just doing one. Now, they want us to write the, identify the equation. If you have a quadratic function that is graphed, vertex form is the easier of the forms to write the equation because we just need to know the vertex and the a value. So we're going to use the y equals a times the quantity x minus h squared plus k. And what do h and k stand for in this equation? What do they represent? What does the ordered pair HK represent? Not the axis, the vertex. That's why it's called vertex form. So the vertex is h comma k. Well, we already know that the vertex is -1, -9. Now, we could solve for the a value, but I'm going to show you a little trick here. If from your vertex you go up 1 and over 1 to your next point, that means your a value is 1. If you have to go up if you go up more than 1, then we know we have a different a value. But because I go up 1 over 1 to get to that first point, obviously it changes after that. My A value is 1 in this case. So when I substitute that in, that means that y equals 1 times the quantity x minus a -1 squared plus -9. Now, we have a little bit of cleaning up to do because we wouldn't necessarily write it in that format. We wouldn't put that 1 out front. If A is just 1, we don't write the 1. And we have a double negative inside here. So we get y equals the quantity x plus 1 squared. Instead of writing plus -9, we would just say minus 9. So that would be the equation of the function. Again, if you're trying to write an equation from a graph, from a quadratic equation from a graph, vertex form is always the easier form to go by because on the graph you can identify your vertex. That makes it a lot easier. All right, graph E we're going to leave alone for right now. The next one we're going to do is graph F. So what would be the family of functions for graph F? This would be exponential, that it starts off really slow and all of a sudden it takes off. So this would be exponential. Now, in behavior, this is a little different. I know as we look at the graph here, it looks like our graph touches the x-axis. It doesn't, because we have to think about an exponential function. We are either multiplying or dividing to get to the next point. And if I'm dividing a number in half, in a third, I'm never going to get to 0. So even though the graph looks like we are at 0, we are not. So on an exponential here, we would say as x approaches -infinity, in this case, f of x approaches 0. It's getting close to 0, but it is not at 0, and it never will get to 0. It'll get really close, but there's no way through division to get to 0 unless you're dividing by 0, which you can't divide by 0. So that's for the left-hand side of my graph. As I move to the left, that graph's going to get closer and closer to 0. On the right, as x approaches infinity, f of x approaches. Again, do my y values go up on the right or do they go down? They go up. My function is going up, so that would be towards infinity. So as x approaches infinity, f of x approaches infinity. We will pick up with the rest of this one tomorrow.